that was written on the 12th of September 2025. Then the duration is 2 hours and max is 100. So scrolling down there, we have got our instructions. Then we're going to quickly dive into our multiple choice questions there, right? So question number 1.1 there reads, which one of the following is the conjugate acid of HPO 2 negative 4, right? So we're looking for the conjugate acid. So for us to be able to define this, to answer this, we need to explain how a conjugate acid is formed, right? So we're going to say a conjugate acid is formed, is formed, formed when a base gains, when a a base gains one proton, one proton. Or just a proton, which is your H plus there, right? So now, in terms of this, what is actually going to happen here in terms of HPO4 to negative is that we are going to add a proton. So if we add a proton there, we're actually going to say plus H plus. Therefore, we're going to get an answer of H2 PO4 negative, right? So it means this now becomes the conjugate acid of this becomes that, right? So in terms of our answer, this is what we're looking for. So in terms of these answers, it means our correct answer is going to be option B. Then we're going to proceed to 1.2, which reads there. 1.2 reads the molar mass of hydrated oxalic acid, hydrated hydraulic acid, oxalic acid, which is the formula COOH 2 like that, and then it has got a mole of what, 128 grams. Then the number of moles of water molecules X present in the hydrated oxalic acid is, so we're asked to calculate the number of molecules X present in the hydrated oxalic acid. So if we're having such a question, we have to start by expanding our COOH there, which is our oxalic acid. So we're given something like this, H with a bracket 2. So it means if I'm to expand that one, I'm going to get a formula of C2 O, or I can say H2 then O. I'm going to have four oxygens like that. Then after that, I'm supposed to calculate the relative molecular mass of the COO. Let me just say C2 for it to be easy. I'm going to say C2 H2O4, right? So in terms of this, I'm going to say my carbon has got a mass of 12. So carbon 12 plus 2 multiplied by 2 there, because we're having two carbons. Then I'm going to say plus hydrogen has got a relative atomic of 1 multiplied by 2 hydrogens there, plus my oxygen. My oxygen has got a relative atomic mass of 16, then multiplied by 4, right? So if I'm to do my math there, I'm going to get an answer of 90 grams per mole, like that. Then after this now, we need to calculate the relative molecular mass of this, right? So I'm going to say this one is equivalent to 90 plus 18x, right? Plus 18x there, 18x, right, is equivalent to this value, which is 126, right? Is equivalent to 126. Okay, so someone might actually wonder where I got my 18 from, right? So this is how I actually got my 18. So it means here hydrogen has got a mass of 1 multiplied by 2, then plus 16, which is multiplied by 1, which is my oxygen. Therefore, I'm going to get an answer of 18 grams per mole there for water. Therefore, now I'm supposed to make this X the subject of the formula. It means I'm going to say my 18X is equivalent to 126, then minus 90. Therefore, I'm actually going to get a value of 18X is equivalent to, so if I do my math there, I'm going to get a value of 36. Therefore, now we have to make 18x the subject of the formula. For me to make x the subject of the formula, I'm going to say my 18x is equivalent to, 18x is equivalent to, therefore I'm going to say is equivalent to, if I can say 36 there, therefore what do I do there? I divide both sides by 18 to make x the subject of the formula. Therefore, my final answer there for x is equivalent to 36 divided by 18. We're going to get a value of what? Of 2. So B is my correct answer. Then I'll proceed to question 1.3. So question 1.3 there reads 10 moles of zinc we're given 10 moles of zinc there, is allowed to react with 5 moles of HCl. Then in a test tube, according to the balanced equation below, so this is the balanced equation that we are having, then we are asked in terms of how many moles of HCl and zinc chloride are in the test tube after the completion of this reaction. So now to formulate that we need to start by using the mole ratio. I will use the mole ratio between zinc and HCl. According to the balance equation there, I'm going to say my zinc there is to the other one, which is my HCl there. So zinc versus my HCl there, I'm going to say my HCl there. Therefore, my zinc there, according to this balanced equation, is 1 is to 2, right? So is 1 is to 2 if I'm to use that coefficients there. Therefore, what are we given in terms of my zinc there? I'm having 10 moles. So for zinc there, I'm going to have 10 moles. Then here, it means if I'm having 10 moles of zinc, how many moles should I actually make use of this side? It means I'm supposed to be getting, 20 in terms of this ratio. So it means here 10 moles of this side, the ratio is 1 is to 2. If I'm having 10 for zinc, I should be having 24 for HCl. Then after that now, in terms of this, what are we given in terms of HCl? So we only have Roman. So for zinc there, I can just like say we only have how many moles according to what we are given? We are only given 5 moles of HCl. Then I'm going to say there, therefore my HCl, according to this, HCl is the limiting reagent there. So it's my limiting reagent or limiting reactant. Then having said that, now I'm going to say the available moles of HCl. So the available moles of HCl there is how many moles? 5 moles. So moles available for HCl, available moles of HCl, I'm going to say is equivalent to 5 moles, right? Then after that, I'm going to say, so for me to get the one for zinc, I'm going to say for zinc chloride there, zinc chloride Cl2 formed is equivalent to, I'm going to say formed is equivalent to 5 all over 2, right? I'm going to divide by that by 2. Therefore, I'm going to get a value of what? 2,5 moles, right? So I'm going to say 2,5 moles. Then after that, now the amount of zinc that is consumed. So zinc consumed, Zn, I can put in bracket and say the one that is consumed in terms of zinc. What am I going to get there? Is equivalent to also 5 all over 2, right? Therefore, I'm going to get a value of 2,5 moles. So it means we consumed 2,5 moles of zinc according to this ratio there, which is 1 is to 2, right? Then to scroll down there for some space, let me erase that there. So in terms of that, now I'm going to say the leftover reactants and products. So what was actually left over? So leftover in terms of reactants, I'll say R and products, which is my P, right? So it means here HCl that was left after, I'm going to say HCl left there is equivalent to, so I started with what? 5, and then how much did I consume in terms of what? HCl. I used all of it, therefore I'm going to get a value of what? Of 0 moles there. So it means I consumed all of my HCl. Then after that, I'm going to say the amount of zinc left after the reactant there, the reaction, I'm going to say zinc left is equivalent to how many moles? So I started with, with 10. Then how much did I consume there? I only consumed 2,5. Therefore, it means now what am I remaining with? I'm left with 7,5 moles. So 7,5 moles of zinc were actually left. Then after that, now I'm going to say the amount of zinc chloride formed on the side on the product. So amount of zinc chloride, amount of ZnCl2 formed, right? So this is the amount that was actually formed on this side. I'm having a value of 2,5, right? So it means now in terms of this, now we can go ahead and look at our answers there, right? So it means now how many moles of hydrochloric HCl and zinc chloride are in the same test tube after the completion of the reaction, right? So in terms of our calculation, we see here in terms of zinc of HCl, how much was actually left? We were left with 0. So I'm going to tick those boxes then. Then on this other end here, how many moles were actually left for zinc chloride? We are going to have a value of 2.5, right? So it means this one is already out. Therefore, my correct answer there is actually going to be B. So letter B is our correct answer. Then I'll proceed to question 1.4. So question 1.4 reads there, the number of hydrogen atoms present in 1 mole of ammonia NH3 is, right? So we're looking for the number of hydrogen atoms in 1 mole of NH3 is. So in terms of this now, we're going to say each molecule of NH3. So in terms of this, I can just say each molecule of NH3, each molecule of NH3, molecule of NH3 there. Okay, so here's how many hydrogens? Here's 3 hydrogen atoms. There's 3 H atoms, right? So where do I get this from? I'm getting it from NH3 then. Then after that, we're going to say how many moles? So 1 mole of NH3. So I'm going to say 1 mole of NH3. 1 mole of NH3 contains how many? Contains, right? So in terms of my Avogadro constant there, I'm going to say Na there is equivalent to 6,02, 6,02 times 10 to the power 23 molecules, right? Molecules like that. So if I'm having that, now it means now the total number of hydrogen atoms. So total hydrogen atoms there, total hydrogen atoms, what am I going to get there? I'm going to say is equivalent to 3, right? Because I'm having a total number of what? Of 3 in terms of that, multiplied by that constant, which is 6,02 times 10 to the power 23 molecules, right? So if I can multiply that one, I'm going to get a value of 1,806 times 10 to the power exponent 24. So it means my correct answer is going to be option C there. Then the others are going to be wrong. Then I proceed to 1.5, which reads 1.5 reads 2,5 moles of carbon dioxide gas at HTP has got a volume of. So in terms of this, I'm going to say what's the volume of this? I'm going to say 1 mole of any gas to just explain there. 1 mole of any gas, 1 mole of any gas, right? Is equivalent to or occupies the 22,4 dm cubed, 22,4 dm cubed, right? So this is the volume that it occupies under STP, right? Then after that, I'm going to say for 2,5 moles there, then for 2,5 moles, what are we going to get? 2,5 moles of carbon dioxide of CO2. Therefore, I'm going to say by formula, you know, our N is equivalent to V all over Vm, right? Therefore, to substitute with the values there, what am I looking for? Do I have the number of moles? Yes, I'm going to say the number of moles is 2,5, therefore is equivalent to the volume. So that's the volume that I'm looking for, which is V all over 22,4, right? So which is the molar gas volume, right? Therefore, I'm supposed to cross multiply. So V is equivalent to 2,5 multiplied by 22,4. Therefore, I'm going to get a value of 56.0 there. So 56,0, which is now in what? In dm cubed, right? So it means my correct answer is going to be option C for 1.5. Then question 6 read there, in a chemical reaction. So we're given a chemical reaction, the difference between the potential energy and the products, the potential energy and the products of the products and the potential energy of the reactants is equal to. So now we are having option A that says the heat of reaction, right? So this is the heat of a reaction, right? So then this one says rate of reaction, which is incorrect. Then C, activation energy is incorrect, and then total potential energy of the product is also incorrect. So our only correct option there is going to be option A. Then 1.7 reads the chemical reaction that represents an endothermic reaction, right? So an endothermic reaction, the most important thing there that we need to know in terms of the endothermic reaction is that your delta H is actually going to be what? To be greater than 0, or your delta H is going to be positive, right? So now let's look at these values that you're given there. We need this one plus heat, so it means it gives out heat. That's an exothermic reaction. And then here is delta H less than 0 is also an exothermic reaction. And then option C, also a negative there, is also refers to an exothermic reaction. But the last option there greater, delta H greater than 0, it means this is an endothermic reaction. So our correct option there is going to be option D for question 1.7, and then the rest are actually going to be wrong there. Then we proceed to the next question, that is question 2. It is the define the term concentration of a solution. So we are asked to define the term concentration of a solution, right? So how do we define the concentration of a solution? Concentration of a solution is defined as the number of moles. So I'm going to write it down there. The number of moles, the number of moles, the number of moles, the number of moles of solids per unit volume, per unit volume. That's how we define our concentration. Then 2.2 is there, calculate the concentration. So we're asked to calculate the concentration of the solution, of a solution containing 4,4 grams of magnesium hydroxide dissolved in 200 cubic centimeters of what? Of water, right? Therefore, now we're actually going to say our option is going to say for 2,2, 2,2 there, allow me to use this page there, 2,2, right? So in terms of this, we're going to say by formula, your concentration is equivalent to the mass all over mv, right? So therefore, we're actually going to say this is equivalent to the mass that is provided here is 4,44 grams. Therefore, I'm going to say 4,4, is it double four? Yeah, 4,44 grams all over the m there, which is the molar mass, right? So if you had to calculate the one for your magnesium hydroxide there, it means now we are going to say how many there. We're going to say your mg, your mg, your mg. Let's look at our magnesium, which is 24. We're going to have a value of 24 for mg there, 24. Then bracket there, we're going to add, and then in terms of that, it means we're going to have 16 times 2. So 16 times 2, which is 32. And then we're also going to have what? 1 times 2, like that. So if we're to do our math there, we're going to say this is same as 32 plus 24, then plus 2, right? So we're going to get a value of what? Of 58 for the molar mass of magnesium. Therefore, I'm going to say 58 there, then multiplied by the volume, right? So according to this, the volume that is given there, can you see, is in cubic centimeters. So we're going to convert to 200 cubic centimeters to 2 dm cubed, right? So for us to do that, they were supposed to say 200 divided by 1,000, which is equivalent to 0,2. So it's going to be 0,2 dm cubed, right? So we're going to substitute that 0,2 there. So 0,2. Then if we're to do our math there, 4,44 divided by 58,02, we're going to get a value of 0,38. And then I'm going to say mole per dm cubed, right? Take note of the units of measurement for concentration. It's going always to be mole per dm cubed. Then we proceed to question 2.3. So question 2.3 is there. Calculate the concentration of hydroxide ions present in magnesium. Calculate the concentration of the hydroxide ions present in magnesium hydroxide solution. So we are asked to calculate the concentration of that of OH, right? So in terms of this, I'm going to say my concentration 2.2.3. I think the other one was 2 point, oh, it's just 2.3. So it's 2.3 there. I'm going to say question 2.3. So 2.3 there. So 2,3, right? So in terms of this, we're asked to calculate the concentration of this. So I'm going to say here my concentration of magnesium hydroxide. Remember the square brackets in chemistry, they refer to our concentration, right? I'm going to say OH there, 2 there is equivalent to how many? So according to the ratio, it's going to be 2 OH, right? So OH negative, like that. Then after that, I'm going to say the number that I'm given there is actually going to be 2, right? Then multiplied by this concentration. So it's going to be, the ratio there is more of like double the hydroxide, right? So it means here I'm going to say 0,38 multiplied by this concentration that I got at the top there, 0,38, right? Therefore, I'm going to get a concentration of what? 0,76. So 0,76, then the units of measurement, mole per dm cubed like that. Then we are done with question 2.3. Then we're going to proceed to the next question, which is our question 2.4 there. They're asking us to determine the percentage composition of water of crystallization in hydrated copper sulfate, right? So this is our copper sulfate, right? So now to work this one out, we're going to go to this page again. This is now our question 2.4. Allow me to scroll a bit. So 2.4 there is, I'm going to start by calculating the molar mass of copper as sulfate, right? So M there, right? Then I'm going to say the mass of copper sulfate on the side CuSO4. So allow me to break it into parts, right? So I'm going to say my copper according to my periodic table there. Where's my copper is supposed to be somewhere there, which is 63.5, right? So I'm going to say my copper there is 63.5, 63.5 multiplied by 1, then plus again my sulfur, which is 32. Just to confirm there, my sulfur is 32. Therefore, I'm going to say 32 multiplied by 1, 32 multiplied by 1, then plus my oxygen, which is equivalent to 16 times 4, right? So it's going to be 16 multiplied by 4, which is going to give me a total of 159.5, 159.5 grams per mole, right? So I'm going to like get that answer there. Then after that, now I'm going to calculate the N of 5H2O, right? So the N of 5H2O there, I'm going to say the molar mass of 5H2O there, I'm going to have 5H2O like that, right? 5H2O. Therefore, I'm going to say this is equivalent to 5. Then I'm going to put a bracket there. So it's actually going to affect everything inside this bracket, right? So basically, the molar mass of water there is actually going to be what? To be 18. Therefore, I'm going to say 5 multiplied by 18, which is going to give me a value of what? Of 5 multiplied by 18. So it's 5 times 18 there. I'm going to get a value of 90. Therefore, this is going to give me a value of 90. I'm going to say 90 grams per mole like that. So this is my 90. Then after that, now it means now I'm having this 90 and then this 159.5 there. Therefore, I'm going to proceed to say in terms of the percentage of water, I'm supposed to add the totals, right? So I'm going to say on this side here, I'm going to say 159.5, 159.5 plus a 90 there. So I'm going to get a value of how many there? If I add, I'm going to get a value of 249, 249.5, right? So in terms of the percentage there, so the percentage of H2O is equivalent to, so I'm going to say is equivalent to the 90 that I got for water there all over the total there, which is 249.5, then multiplied by 100 to formulate a percentage. Therefore, I'm going to get a value of 36.07, 36.07% like that. Then I'll proceed to the next question after 2.4. So I'm proceeding to question 2.5 there. So question 2.5 reads, the following reaction between hydrogen and nitrogen takes place in a closed system at constant pressure and temperature. So we're having that reaction there. Then we're asked to state the Avogadro's law in what? In words, right? So here it says the 1 mole Avogadro's law states that 1 mole of any gas, 1 mole of any gas, okay, of any gas occupies the same volume, occupies the same volume at the same temperature and pressure. At the same temperature and pressure. So this is how we actually define our Avogadro's law. Then 2.5.2, they're saying if 12 dm cubed, so we're given a value of 12 dm cubed there of H2 and 6 dm cubed of N2 are used, calculate the total volume of the gases at the end of this reaction. So in terms of this, I'm going to say start with the ratio from that one there. Allow me to use this page. I'm going to say the ratio there. I'm going to say ratio. So my ratio is going to look like this. So my ratio between my H2 and my N2 there. So in terms of this is my H2 versus my N2. So my H2, I'm going to say H2 this side. So the ratio H2 versus my N2 like that. So in terms of this balanced equation, we can see the ratio there is 3 is to 1. So I'm going to say this side 3, then on this other side, I'm going to get a value of 1. Right after that now, what else do I have in terms of this? They are saying 12 and 6 is actually used. Therefore, I'm going to say on this side is 12, and then this side is going to be 6, 12, and a 6 like that. Then after that, this is the given volume, same as, so if I'm to break down, this one is same as this versus this, right? If I'm to break it down, this is same as 2 is to 1, right? So the ratio is same as 2 is to 1, right? So now the required is 3 is to 1. So the required, according to the required, so that top part there. So this is more of me saying what required there, right? So this is the required. Then after that, now I'm going to say N2, therefore N2, I'm going to say therefore N2. Therefore, N2 there, I'm going to say N2 is equivalent, is in excess. In terms of this, we can see our N2 is in what? Is in excess, right? So I'm going to say N2 is in excess, right? So we're having an excess reagent in terms of what? N2. Then our H2 is actually going to be our limiting reagent, right? So H2 is limiting reagent, right? So I'm going to have a limiting reagent in terms of that. Then after that, I'm going to proceed to say, according to the reaction of the limiting reaction, so available, what are we actually having in terms of the available, in terms of the limiting reagent, which is my H2, right? So available there is equivalent, available limiting reagent, which is my A2, is equivalent to, I'm given a value of 12 in terms of that there. So this is my 12 dm cubed. Therefore, I'm going to say 12 there is equivalent to, so H2 is equivalent to 12, right? So from the ratio, from the above ratio where we're having 3H2 is to N2, right? So 3 is to N2. Then we're also having what on the side? 2NH3, right? 2NH3, right? That's the reaction there. We're adding this to that, then to get that one there, right? So for 12 volumes of H2, so if we're having 12 volumes of 12V of H2, then what is going to happen is that the N2 that is consumed is equivalent to, so I'm going to say N2 consumed, N2 that is consumed is equivalent to 12 over 3, right? So according to that equation there, 12 all over 3, so 12 all over 3 there, then multiplied by 1, right? Multiplied by 1. So I'm going to get a value of 4, right? So this is the volume that I'm going to have there. So I'm going to say 4 in terms of the volume. Then the NH3 that is going to be produced, NH3 produced. So NH3 produced there, I'm going to get a value of what NH3 produced is equivalent to also 12 all over 3 multiplied by 2, right? So multiplied by 2. Why am I multiplying by 2? Because the mole ratio says 2 there. Then I'm going to get a value of what? If I do that, I'm going to get a value of what? 8. So I'm going to say 8 volume there. Then after that now, I'm going to say H2 that was left there. So H2 left, H2 after the reaction has ended, H2 left is equivalent to 12 minus 12, right? So which is equivalent to what? To 0, right? So this is the final volume that we are having there. So for final volume, then for H2, then after that, I'm also going to say the N2 that is left there. So the N2 that is left, N2 left is equivalent to, so how much did I start with there? I started with 6, then consumed 2. Therefore, I'm going to get a value of what? 6 minus, sorry, I consumed 4. Then I'm going to get a value of what? 6 minus 4, which is equivalent to what? To 2V, right? So it means now the total volume that is actually going to be left there, I'm going to say 0, 0 plus 2 and then plus 8 there, right? So 0 plus 2 plus 8, which is equivalent to 10 dm cubed, which is equivalent to 10 dm cubed. So that's the total volume that we're looking for, which is equivalent to 10 dm cubed like that, right? So then to proceed to the next question, I'm going to say we are on question 2.6 there, right? They're saying calculate the mass of butane gas CH4 at STP if it occupies a volume of 4,480. Therefore, I'm going to say in terms of this year, what am I having? So I'm going to start by saying the number of moles. Allow me to use this page again. So I'm going to say the number of moles of what? So I'm going to calculate C. They're saying 4H 10 there, right, is equivalent to V all over Vm, right? Therefore, I'm going to proceed to say this is equivalent to 4,48, 4,48 all over. So this is the volume that is given there, which is 4,48 there. This is the volume that is given all over there. My Vm, which is a constant, right? So molar gas volume there, 22,4 at STP. So I'm going to get a value of what? 0,2. So it's 0,2 moles if I divide that one. Then after that, I'm going to say the number of moles is equivalent to M all over M, right? So M all over M, right? So what are we looking for there in terms of that? It means the other one is going to be our C4H10, right? So CH410 there, right? Calculate the mass of butane gas that is occupied. It's a at STP if it occupies a volume of that, right? So I'm going to say here, you can see, then to proceed there, I'm going to say this is equivalent to the mass that I'm actually looking for is equivalent to M, right? So then the number of moles according to the calculated at the top there is going to be 0.2 all over M, right? So the molar mass of this C4 H10 is equivalent to carbon has got a mass of 12 multiplied by 4, then plus my hydrogen 1 times 10 there, which is equivalent to a total of 58, right? So I'm going to get a value of 58. Therefore, I'm going to say all over 58. So if I do my math there, I'm going to get a value of 11,6 grams. So I'm cross multiplying 0,2 multiplied by 58. Then I'm going to proceed to question 3. So question 3 reads, oleic acid is a long chain carboxylic acid, which is the part of the regular human diet, being present in animal fats and vegetable oils. A laboratory analysis of this compound shows that it has the following chemical composition. So we're having carbon, hydrogen, as well as oxygen, and then we're given in terms of the percentages, right? So now, with the first question there, it says define the term empirical formula, right? So the empirical formula is the simplest whole number ratio. So the simplest whole number ratio, simplest whole number ratio, simplest whole number ratio of atoms in a compound, of atoms in a compound, of atoms in a compound. So that's the empirical formula, right? Then the next step there, we're asked to determine the empirical formula, right? So I'm going to just like formulate a table for this empirical formula there. So I'm going to say here what we're having carbon, hydrogen, and oxygen. Therefore, I'm going to say my carbon here, then my hydrogen here, and lastly my oxygen, like that. Then split it into three parts, like that. Okay, so now the first thing that I'm supposed to get there is the masses of each, right? As a percentage is 7660. So this one is 7660, 76.60. Then for hydrogen, what we have 12.05, 12,05. Then the last one that we're having for oxygen is 11.35. So 11,35, right? So now we're supposed to use these percentages to calculate our number of moles, right? Remember, by formula, N is equivalent to M all over M, right? So I'm going to divide by the relative atomic mass of carbon, which is 12, then for hydrogen is 1, then for oxygen is 16, right? So if I divide there, I'm going to get a value of what? At the top there, 12, 7660 divided by 12, I'm going to get a value of 6,383333, like that, right? Then on this other end, I'm going to get, if I divide a number by 1, it retains its original value. Then the last one, the 1135 divided by 16 gives me a value of 0,0,70. 9393, I can just say 75. Yes, that's how we actually get the numbers. Then after that, now, so if we get here, we're actually going to divide by the smallest number of what? Of moles, right? So in terms of this, I'm going to retain this one, which is 6,3833, right? 3 all over. So the smallest there is going to be 0,7. So I'm going to say 0,709375. Then here I'm also going to say 12,05 all over that value, which is 0,709375. Then on the last one again, I'm going to divide by the same value because it's the smallest value. then all over 0.70937.5, right? So if I divide there, I'm going to retain a value of 1. Then if I divide 12.05 divided by that value, I'm going to get a value of what? 16.98. Therefore, if I round it off, I'm going to get a value of what? 17. Then the last one there, I'm also going to say 6.3833 divided by that value. I'm going to get a value of 8.9 something, right? 99, right? So I'm going to round it off to give me a value of 9 there, right? So this is what you are going to get there in terms of that, right? So this is the ratio that we have. Then after this, now I'm going to say this is my ratio there, right? So this is the ratio that I have. Then in terms of the empirical formula, it means my carbon, I'm having 9 carbons. Then my hydrogens, I'm going to have 17. Then lastly, my oxygen, I'm only having 1. So this is what I'm going to get in terms of that question there. Then to proceed to question 3.13 there, it says determine the molecular formula if the molar mass of the compound is 282 grams, right? So we're given that is 282 grams. So it means now what I'm going to do there is to calculate the molar mass of this that I'm given there. So it's question what there is question 3.13. So I'm going to say 3.13 there, right? Let me underline that there. So 3.13. So I'm going to calculate the molar mass of this, which is C9 H17 with oxygen, right? So this is equivalent to 12 multiplied by 9, which is my carbon there, plus my hydrogen, which is 1 multiplied by 17, then plus my oxygen, which is 16 times 1, right? 16 times 1. Therefore, what am I going to get there? I'm going to get a value of, this is equivalent to 141, right? So that's the value that I'm going to get there. So it's 141 grams per mole if I'm to include the units of measurement there. Then after that, what am I given there is the value. So I'm given a value of the compound with a mass of 282 grams per mole. So I'm going to take this 282 and then divide by, so I'm going to say 282, then divide by 141, right? So 141, therefore I'm going to get the number of moles as what? 2, right? So this 2 is going to affect this whole C9H17, then O, right? So I'm going to say multiplied by 2, right? So if I multiply by 2 there, it means I'm going to get a value of what? C18 there. Then my hydrogen there, 17 times 2, which is 34. And then my oxygen, I'm going to have a value of what? Of O2. Then we're done with question 3.13. Then I'll proceed to the next question, which is question 3.2, right? So 3.2 reads there, a sample of impure calcium carbonate limestone of unknown mass requires a continuous supply of strong heat to decompose according to the following balanced equation. So this is the balanced equation that I'm having. Then after the completion of the reaction, then we're left with, it says 11.76 grams of carbon calcium oxide was produced or was formed, right? So then we are given the percentage purity of calcium carbonate is found as what? 80%. Then we are asked to calculate the mass of the impure calcium carbonate, right? So for us to calculate this one, 3.32, I'm going to say here I need space 3.32 like that, right? So for me to calculate that one, we are going to say here, let's start by calculating the number of moles of calcium, number of moles of calcium oxide. So number of moles of calcium oxide is equivalent to, remember by formula, number of moles is equivalent to M all over M, right? So what do I have there in terms of this? So I'm going to proceed to say there N is equivalent to, if I say N is equivalent to, therefore N is equivalent to, let me just like go there. What do I have? I have a value of 11.76. Therefore, I'm going to say N is equivalent to 11.76, right? 11.76. So it's 11.76 all over this, the mass that is given, right? So for calcium oxide, remember I can say the molar mass of calcium oxide there, CaO, is equivalent to, calcium has got a mass of 40 multiplied by 1, then my oxygen there is 16 multiplied by 1, right? So if we do the math there, we're going to get a value of what? 56, and then grams per mole like that. Then 11.76 there, therefore I'm going to say divided by 56, right? So if I divide there, I'm going to get my number of moles. N is equivalent to 0.21 moles, right? Then to proceed to the next part there, I'm supposed to use the mole ratio between my calcium oxide versus my calcium carbonate versus my calcium oxide there, right? So I'm going to say this according to the mole ratio there. So I'm going to say to scroll down there and say my N there for calcium oxide versus the one for calcium carbonate, right? CaCO3, right? So according to this balanced equation there, the mole ratio there, it shows that is 1:1. Therefore, I'm going to say the mole ratio here is 1:1, like that, right? So if I'm having that, then it means here, what do I get there? I got for calcium oxide 0.21. It means also this side I'm going to get a value of 0.21. Then after this now, I'm going to say the number of moles of calcium carbonate is equivalent to, so the number of moles of calcium carbonate there is equivalent to M all over M, right? So we're looking for the what? For the mass there, right? So it means my number of moles there, I'm going to substitute with 0.21, then M all over, then the molar mass of calcium carbonate. I can start by saying calcium has got a mass of 40 multiplied by 1, then say plus there, bracket, my carbon is 12 multiplied by 1, because only one carbon I have there, then multiplied by 16 multiplied by 3 there, right? So oxygen is 16 multiplied by 3, right? So to cross multiply, I'm going to say my mass there, M, is equivalent to, therefore I'm supposed to cross multiply this value with that one. Then I'm going to get a value of what? Of 21 grams, right? 21 grams. This is the mass that I'm actually having. But remember, we asked to, we were given the percentage purity of calcium carbonate as being what? 80%. Then we are supposed to calculate the mass of the impure carbonate, right? Therefore, it means here which one is impure calcium carbonate, right? So to proceed to that, I'm going to say here, let's say percentage purity is equivalent to, so I'm going to get that value there, which is 80. Therefore, I'm going to say my 80% there is equivalent to the one that is actually pure, there is 21 grams out of it, right? All over the impure one, right? I can just say that is my x there because I don't know it, then multiplied by 100, right? So to make 100x the substitute of formula, I'm going to get something like 80x is equivalent to, if I multiply there, I'm going to get 2100, right? So divide both sides by 80 divided by 80. Therefore, my x there is going to give me a value of what? X is equivalent to 26,25, right? So I'm going to get a value of 26,25, right? Grams, right? So it means this is the mass of the impure calcium carbonate. Then we proceed to the next question, which is our question number 4. So question number 4 reads the 14,5 grams. So we're given 14,5 grams of iron reacts with 12 grams of water during a corrosion reaction to form Fe3O4 and H2 according to the following unbalanced equation, right? So this equation is not balanced there. Then we are asked to define the term limiting reagent, right? So this is a reactant that is used up first, right? So a reactant that is used up first, that is used up first, and it determines the amount of product that is going to be formed, and determines the amount of product formed, like that. So this is how we define our limiting reagent. Then the next question asks us to balance our Fe. So our equation there is Fe, then H2O, okay, plus there H2O to give me a value of what? Fe 3O4 plus my H2O, right? So in terms of this, you can see here I'm having, on this side, I'm having 3 ions, and then this side I'm having only 1, right? So for me to balance there, I should multiply with the coefficient of what? Of 3. Then, so my ions are now balanced, right? Then to move on to the next part, what do I have? I am having 4 oxygens, and here I'm having only 1, right? So for that, then I'm going to multiply by what? By 4, right? So it means if I multiply by coefficient of 4, now I'm having 8 hydrogens. Therefore, this side I should also balance with what? With the 4, for me to get a final answer of 4H2, so that I can also have my 8 hydrogens. Then I'm going to proceed to question 4.3. 4.3 says determine the limiting reactant, right? So we're asked to determine the limiting reactant, right? So for us to determine the limiting reactant, we're going to proceed and say there, according to this, from the balanced equation there, I'm going to say the number of moles that I actually going to have there. I'm going to say step number 1 there, I'm going to use the mole ratio that we are having there. So it's Fe in terms of with H2O, right? So H2O, these are my reactants. Then according to the balance equation there, it means it's 3:4, right? So 3:4 like that, right? So I'm having a value of 3:4. Then after that, now I'm supposed to calculate the initial number of moles of each, right? So the number of moles of Ne, I'm going to say the number of moles of Ne is equivalent to how many there? I'm going to say number of moles, so number of moles of Fe, a number of moles of Fe is equivalent to Fe, determine the limiting reagent. So number of moles of Fe there is equivalent to M all over M, right? So what am I going to get there? I'm going to get a value of what? So what do I have there in terms of the mass? For Fe, which is my ion, is 14 there. So I'm going to say 14, 5 all over. So the molar mass of ion there, if we refer to the periodic table, we're going to get a value of what? Of 56, right? So if I divide there, I'm going to get a value of what? 0, 2, 5, 8, 9, right? So these are the number of moles that I actually get from that one there. Then after that, now I'm going to say in terms of this, the H2O, in terms of the H2O again, number of moles of H2O is equivalent to M all over M, right? So M all over M. Therefore, what do I have in terms of the mass for water there? I'm given a value of what? Of 12 at the top there, all over the molar mass of water, which is my 18, right? So if I do my math there, I'm going to get a value of the number of moles of water, which is equivalent to 0,667 6667. Okay, I can just like write it like that. So 0,25 also moles, right? So these are the moles that I'm having in terms of this, right? Then after that, now I'm going to compare the mole ratio again, right? So I'm going to compare the mole ratio between this and that, right? Between my ion and my H2O, right? So let me just like use a different color so that it can be easy for me to identify these ones. I'm going to have my Fe there. So my Fe there versus my H2O. My Fe versus my H2O. So what I'm going to get there is a value of what? So the mole ratio is going to be 3:4 according to our balanced what equation there, right? So what do I have there? It means on this other one, I'm having a mass of what? Of 6,0,66, right? I will start with water. I'm going to have a value of 0,667 there, right? So this is actually what I actually have, right? So what I actually have, right? So in terms of this, how much am I going to need in terms of this? So in terms of this here, I'm supposed to say 3/4, 3/4. So for Fe, I'm going to say 3/4 multiplied by 0,67, right? Multiplied by 0,6667, right? So I'm going to get a value of what there for my ion. I'm going to get a value of let me just like do this quickly. 3/4, so it's 3 divided by 4 multiplied by 0,667. Okay, so it gives me a value of 0,5, right? So this is what I need in terms of this. I only need 0,5, right? So how much do I have? But for ion there, I'm having a value of 0,25, right? So automatically it shows that this is the one that is the limiting reagent. So the one that is the limiting reagent is going to be this one, right? Because how much do I have? I'm only given there, according to my moles, I'm given 0,2589. Then what do I actually need there? I need 0,5. So I do not have this 0,5, right? So if you are to want to prove again, you can go and say H2 like that, right? Then the mole ratio there is 3:4. Then on this other end there, we are going to say, what do you have there in terms of this? We are given 0,2589, right? So to get this one here, you are going to say the number of moles for H2 is 4/3 multiplied by 0,2589, right? So if you have to do your math there, you are going to get a value of let me just quickly do it again. 4 divided by 3 and multiplied by 0,2589 is equivalent to, so my value there is going to be 0,34, right? So 0,34 52, right? 52 moles, right? So according to this, you can see they at the start, how many moles do I have in terms of my ion there, right? My water there. So I'm having 0,66. So it means this one is in excess. Therefore, my limiting reagent there is going to be my my Fe. So my Fe is the limiting reagent. Then I'm going to proceed to question 4.4. So that says they calculate the mass of FeO3 O4 that will be formed, right? So we need the mass there. So I'm going to say question 4 there. This is question 4.4. So I'm going to underline there and proceed to question 4,4. So 4,4 is equivalent to, so we're looking for the amount that is actually going to be formed, right? So I'm going to say the number of moles there of Fe3O4, right, is equivalent to M all over M, right? M all over M, like that, right? Therefore, which value I'm going to use there? The number of moles. So the number of moles that I'm going to use there is going to be 0,086. So 0,863 is equivalent to M all over the molar mass, right? So the molar mass of this one there is going to, if I do my math, I'm supposed to get a value of 232. Therefore, I'm going to cross multiply there and I'm going to get a value of 20,02 grams, right? So this is the value that I'm going to get there, right? Then the question might arise as to how do I get the 0,8063, right? So I'm actually going to say in terms of my limiting reagent, remember my Fe is my limiting reagent, right? So Fe versus FeO3, right? So FeO3 there, according to the balance equation, is 3:1, right? So the mole ratio there, Fe 304, right? So this is 3:1 according to our balanced equation, right? So here in terms of this, how many do I actually have there? It means here I was having a value of 0,2589, right? Therefore, I wanted to find this one there. Therefore, I'm going to say 1 over 3 multiplied by 0,2589. Therefore, I'm going to get a value of 0,0863, right? So this value is the one that is the number of moles of Fe3O4 there. Then I'm going to proceed to the next question, which is now our question number 5, right? So it says the calcium carbonate and excess what hydrochloric acid. So we're having these two compounds there react in a reaction vessel. Then the balanced chemical equation is given as follows, right? So this is the balanced equation that we are having there. Then we are saying consider the potential energy graph for this reaction as illustrated below. Then it says 5.1. The graph has been labeled 1 to 4 there. 1 to 4, 1 to 4. 1 to 4 to represent the various energies that are illustrated by the energy profile. Identify each of these energies on the profile, right? So there we are asked to identify all those that are actually labeled there in terms of what? Of 1 until 4, right? So 1 there, it says here it's going to be the energy of the reactants, right? So I there is energy of reactants like that, right? Then my 2 there is going to be my activation energy. So let me just write it there. So my 2 there is activation energy. Then to proceed there, I'm going to have my 3, right? So my 3 there, this is the one there. So between that the activated complex and the energy of the product there, I'm going to have what we refer to as the energy that is released. So I'm going to say energy released, released like that. Then my 4 there is going to be the energy of the products, right? So my 4 there is actually going to be energy 3 4. So there is going to be the energy of the products. Then the seed until 5. So my 5 there is my enthalpy, right? So I'm going to say enthalpy, which is referred to as sometimes the heat of reaction. So we're done with question 5.1 there. So then we're asked to define the term activation energy, which is the minimum energy needed for a reaction to start like that. Then we're actually going to proceed to question 5.1.3. It says provide a name for label B, right? So we're looking for label B there at the top there. So it says here for label B and what significant process takes place at this point, right? So the top part there, at the top there, we refer it to as the activated complex, right? So activated complex, right? So what's an activated complex there? So by saying what significant process takes place at this point. It's more of them asking us to define an activating complex, which is an unstable transition, unstable transition from reactants to production to products, or stable transition from reactants to products, like that. So this is our answer for this question. Then we proceed to 5.1.4. It says name the type of this reaction and explain that represents, right? Name the type of the reaction this graph represents, right? Only exothermic or endothermic, and then give the answer, the reason for your answer, right? So according to this, if we look at our graph there, so the energy of the products is less than the energy of the reactants, right? Therefore, it means our reaction is going to be an exothermic reaction. So our answer is going to be exothermic. So for 5.1.4, the answer there is exothermic, right? So for our reasoning there, we're actually going to say your delta H is less than 0. So as a reason there, you can just say delta H is less than 0. Then I'm going to proceed to 5.15. They're saying the same reaction takes place in the presence of a catalyst. Redraw the graph in your answer book and show how the graph would actually change, and then in the presence of a catalyst, right? So this is the original graph that we're having there. So we're having something like this. This is cause of reaction there, and then here what I'm having is my energy. So I'm going to have my energy there. Then after that, it means these way are my reactants according to that there. Yes, and then I'm going to have my products there, right? So this is what I was having in terms of my products, right? So it means now in terms of the activation energy is actually going to what, to lower the activation energy, right? So it means here it's actually going to continue there and then lower it a bit there and then go down and join. Like, remember or take note of the amount of product that is actually going to be formulated is actually going to be what, to be the same. Then we proceed to the question that says how would the presence of a catalyst affect the value of the energy labeled V, right? So let's look at V there. So which is our 5-hour enthalpy, right? So it means now we are asked in terms of the enthalpy, how our catalyst affects our enthalpy, right? So our enthalpy there is no change. It means it's going to remain the same. Remember, the amount of product that is going to be formulated is going to be remaining what, the same, right? So therefore, it does not, a catalyst does not affect. A catalyst does not affect the energy of the reactants, the energy of reactants or products. So we should not always know that the energy will remain the same. It's just like speeds up what, the process. Then 5.2 says the chemical reaction can only take place when the reacting particles are in the atomic state, not molecular state, right? Then particles in a molecular state must be broken down into atomic state by bond energy. Then consider the following reaction. So we're given a reaction of 2Hi to give us H2 plus I2. Then the bond energies required during the breaking of existing bonds and the formation of new bonds are given in the table below. Then after this, now we're asked to define the term bond energy. So bond energy is defined as the energy needed or required energy needed or required energy needed or required to break bonds or overcome bonds there, right? So then 5.2.2, it says calculate the total amount of energy absorbed during the breaking of existing bonds, right? So what you're going to get there is equivalent to the total energy. So remember this ratio there is 2Hi, right? So Hi there, this is the value for Hi, and then we're having this 299, right? So we're going to multiply that 299. Therefore, I'm going to say 2 multiplied by 299 multiplied by 2. Therefore, I'm going to get a value of what? 598. So it's 598 kilojoules per mole, like that. So this is the energy that is needed there to overcome this bond to formulate what? Your H2 and your I. Then it says here, 5.2.3, write down the amount of the activation energy for this reaction, right? So for the amount of the activation energy that we need there, it's going to be the same as this value. So I'm going to say the amount there that is needed is 598 kilojoules per mole, like that. Then 5.4, it says calculate the total amount of energy released during the formation of new bonds, right? So during the formation of new bonds, therefore, we're going to say total energy released. So in terms of this total energy released, I'm going to say total energy released is equivalent to, so total energy released is equivalent to 432, that 432 there. So 432 plus 151 plus 151. Therefore, if I can get the total there, I'm going to get a total of 583. So it's 583 kilojoules per mole there. So this is the energy that is actually needed there, released during the formation of a new bond, right? So you can see these are your products, your H2 and your what, your I2 there, right? So these are the ones that's why we're actually adding them, because they were the ones that were actually released in order to form a new bond there. Then is this reaction endothermic or exothermic? Then we are asked to support our answer by means of what, of calculations, right? So in terms of this, let's just like work it out first, right? So let's work it out, then we're actually going to explain whether it's exothermic or endothermic, right? So it means here delta H is equivalent to energy absorbed, energy, I can just say E absorbed, and then minus E released, right? So it's going to be E absorbed minus E released, right? So I'm going to get a value of what, 598, and then minus my value there, which is released there, which is 583. So 83. Therefore, if I subtract there, I'm going to get a positive value of what, 15 kilojoules per mole, right? So if this is the case, it means now what do I have there? My delta H is positive, right? So if it's delta H is positive, therefore my reaction is actually what's going to be endothermic. Why? I can also give a reason there and say delta H is actually what, greater than 0. Therefore delta H is positive. Then we proceed to the next question, which is question 6 there. So question 6 reads, hydrochloric acid is a monoprotic acid. Hydrochloric acid is a monoprotic acid. Then we are asked to define an acid according to Lowry-Bronsted theory, right? So in terms of this, it means an acid there. How do we define an acid? According to Lowry-Bronsted theory, it means an acid is a proton donor. An acid is a proton donor. An acid, I can just say an acid is a proton donor, right? So by the proton there, remember we're referring to that H plus, right? So H plus ion there. Then 6.1.2, it says give a reason why the hydrochloric acid is referred to as monoprotic, right? So it means it donates one proton, it donates only one proton, right? So it only donates only one proton, which is your H plus what, ion there, right? So strong acid, is hydrochloric acid considered a strong acid or a weak acid, right? So then we're asked in terms of the reasoning behind why it's a strong acid, right? So in terms of this, it means you are going to identify, then after that you are supposed to define a strong acid if you are choosing a strong acid, or if you are choosing a weak acid, you are supposed to define that one, right? So I'm going to say the correct answer there, hydrochloric acid is a strong acid. Then after that, now I'm going to define a strong acid, right? So a strong acid is an acid that ionizes completely. So because it ionizes completely completely in water to form a high concentration a high concentration a high concentration of H3O plus ions. So that's how we define our strong acid. Then to proceed to 6.2, it says the hydrogen carbonate ion can act as either an acid or a base. It reacts with water according to the following balanced reaction, right? So write one word for the underlined phrase above, right? So that can act as either an acid or a base, right? So the correct term there is going to be an ampholyte. So it's going to be an ampholyte. That's our answer there. Then after this, we are going to say 6.2.2, write the formula of the substance that can act as either an acid or a base from the above equation, right? So in terms of this, it means now I'm going to pair this up there. So for me to pair this up, I'm going to say this they can either act as an acid. So it means it can either donate, at times can react, can be in a reaction where it actually donates, and sometimes it can actually but in a reaction that it actually accepts, right? Then the other one there is going to be my water, which is my H2O there. So these are the two that we are looking for. So it's going to be there, the formulas there. I'm going to say HCO3 negative in my water, which is my H2O. Then the final question there, it says copy the equation above and indicate the conjugate acid base pairs, right? So this is what you're having, HCO3 in negative. Okay, that's the state there. Then plus H2O, which is a liquid, then to give us a reversible reaction of H2CO3, then act there. Then I'm going to say plus my hydroxide ions, right? So for easy pairing, they just look at the differences in terms of what the hydrogen what ions or the H plus ions, right? There should be a difference of what of one, right? So in terms of this, you can see HCO3 it looks familiar or looks similar to what to H2O, H2CO3 like that, right? So the difference is only what one hydrogen there. And then again, these ones can be paired together because the difference is just what NH there, right? So it means in terms of this, what is an acid? An acid is a proton donor. And then it means my water there donates there for me for it to be H or H there. It should be what an acid because it actually donated. And then on this other side here, we're going to formulate this one to be a conjugate base, right? So on my OH there is going to be a conjugate base. Then after that, I'm going to say this one, since already I'm having an acid, therefore automatically this one becomes a base. And then the last one there is actually going to become my what? Conjugate acid. So on this side, I'm going to formulate a conjugate acid like that. So this is how you pair all this. Okay, so this is the end of our paper. Hope you enjoyed it. Thanks for watching. Good day, grade 11s. Today we're going to look at a Johannesburg West District control test that was written on the 12th of September 2025. Then the duration is 2 hours and marks is 100. So scrolling down there, we have